All right, we're really continuing in this lesson 4 of Unit 1 to analyze functions. I know a few lessons back it was the title of the lesson was analyzing functions, but we're really analyzing functions in a lot of different ways. In this lesson, we're going to be talking about extrema and average rate of change, which sounds extremely dramatic. It's not too bad. We're going to do a lot of graphing calculator work and then some just hand algebra towards the end. Let's get it done. All right, so a function can be doing different things. I know, shocker, right? So for different intervals along a function, it can be either increasing. So what we think about that is if we were drawing a line that was tangent to the graph at a given point, that's close enough, right? That line would have a positive slope, right? It's going up and to the right. And so if we were to draw a line that kind of was tangent to our function at a given point, it would be increasing. So like from here down is increasing. This graph is increasing. It is going up. It's got a positive slope, right? Or it can be decreasing, right? So that's the same idea. But if we had a negative slope, something like that, if we were to draw a tangent line next to it, and a line that just kissed it in one point, that was too close, but not close enough. If we were to draw a tangent line, probably better off just drawing by hand-ish, right? So if we were to draw a tangent line connected to any point here, it would be going down and to the right. And so it would have a decreasing slope. So this function is said to be decreasing in that interval. So if we look at our kind of example up here, this function is decreasing from here to here, right? So it's decreasing from there to there. And then it starts increasing again from here on to infinity. So it's increasing in this segment. In this segment, we already said it's increasing. It can also be constant. So it can be flat. It can be not increasing or decreasing. So it can have, which if we were to use our slope analogy, it would have a zero slope. Now, you might be thinking, what about something like this that has an undefined slope? Well, that's not a function anymore, and so we're not really talking about that in this lesson, at least, right? That's a relation that isn't a function, and it wouldn't have any slope. It has an undefined slope there. So increasing or decreasing or constant. It can be one of those three things. Let's head on to the next thing. So we're going to use this example to kind of illustrate one kind of problem that you might see for increasing and decreasing. So we're going to use the graph of these functions, there's two examples here, to estimate to the nearest half unit on which intervals the function is increasing, decreasing, or constant. So on this first one, I went ahead and I did. Now, if you're following along with all of my lessons and you're doing them in order, then you will have watched. In the last one, we did a lot of where I go to the graphing calculator and type the thing in. In this one, I made the graphing calculator stuff and I put them as images on here so I can kind of highlight on top of it and we can talk about it and do all those things. Excuse me. So on this first one, this one I did it in a little bit different order. You'll see that in a minute. But on this first one, I went ahead and made a picture of what the graph would look like. So if we graph this, so it's a cubic function, it's a negative cubic function. If you have a lot of your cobwebs dusted off from Algebra 2, you might have been able to look at this equation and figure that out, right? And so that's what the picture looks like. Now, we would look at the picture first and see that this graph, when is it increasing or decreasing or constant? Well, you can see, let me add a layer in here and change my brush to something a little bit different. So if we take a look at this, when is this increasing or decreasing? Well, it's always going down throughout its whole life cycle, right? So it's always going down. It's never going back up. So this one, and if we look at the table, you can see that it does the same thing. So now in this little interval, we could potentially spread this table. I probably should have made this table or made a second table that had even more values down to even really low value, really negative values and really positive values. Oops, excuse me. But, for the sake of this, and what we already know from what this function is going to look like from Algebra 2, this function is increasing from negative infinity to positive infinity. Well, I said increasing, but I didn't mean increasing, did I? I meant decreasing, didn't I? So it is decreasing for all real numbers, right? So it doesn't go up ever, is what it looks like. And we kind of confirmed in this small little space that even in here, there's no jump. Now, we could probably go to halves and get a more granular thing. So if you want to change the step on your calculator to confirm even further that in this little space, because if it changes, it would be in this little space right here, right? If it goes up a little briefly, it would be in this little space. So you could change your step to something smaller and confirm that the numbers are always getting down as x goes up. The y values are getting, the f of x values are getting smaller and smaller. And you could confirm that if you wanted to. So let's take a look at this one, because this one's a little bit different. So if we pull up let me pull these off the screen because we're going to have a little bit more space taken up here. All right, so for this one, I think this is it. If we look at the graph and we graph this, and you could do this by plotting values by hand and whatever else, but you can also plug it into your graphing calculator. So if we graph this on this interval, then this changes. It's got some points where it's increasing and some points where it is decreasing. So it looks like it is going all the way to -1 and doing one thing, and then it's going all the way to +1 and doing something else. So it looks like it is decreasing on this interval, and then it's increasing on the other side of this interval and the other side of this interval. So you might punch into your table and you might pull up something like this. Now, this has the same step values as that last one, but it's kind of hard to see what's going on. Now, you can kind of see because it goes -52, -18, -2, and then up to 2, and then back down to 0, and then back up to -2. So it looks like we can see fairly well, but it's not as granular as we might like it to be, because we really want to look at these different intervals here and see what's going on. So we might look at some different things. So if we pull up these, then we can get a better picture. So this one right here, which actually I'm going to need to take this and pull it to here. Now I can draw where I want to draw. Okay, so if we look here, we've got the interval from -1 to +1. So it goes from -1 down to 1.35, down to 1, down to -1 point whatever, down to -2. So it is in fact decreasing from these intervals, and we can prove it numerically. So if we're writing our answer to estimate, then it is increasing. Let's write the one we just talked about first. It probably makes more sense, yeah? So decreasing from, now you notice that I am writing these in interval notation instead of set builder notation, because we're kind of talking about intervals and we're talking about all real numbers, so it's going to be easier to do that. We're not kind of writing a formal definition of something, so that's why we're using interval notation on these answers. So it is decreasing from there to there, and we can use our tables to evidence that numerically, right? If the problem asks us to do so. And then from -infinity, so I've got this one, see, I changed to a 500 point step, right? So we're getting more and more and more negative as we go this way. We get down to -64 billion, -91 billion, right? So we're getting more and more negative. So, but as we go up, as we get close, as the x's go up, these numbers are going up as well. So we're getting more and more positive as we go this way. So it is increasing here. It's increasing. It's going up during this interval. So from -infinity, so it is increasing from -infinity. Now remember, in interval notation, we never include infinity because we never get to infinity. From -infinity to -1, it is increasing. Now, arguably, these on this end of the -1, at -1, it's kind of it's not increasing or decreasing. That's actually the flat point. That's actually, we'll talk about this in a minute, that's a local maximum. That's the point where it stops. So you could say including, or you could say not including. Probably not including would be a better choice, but you could kind of say either one and make a case for it, because it's increasing all the way up to -1, right? And then it goes down again from there to there. So whether you include them or not include them is kind of subjective on this particular problem. Now, if you're taking this class and your professor or your teacher wants you to write that a certain way and makes an argument for it a certain way, that's fine. You do what they expect you to do. But you could argue that point either way. And so including, not including on the numbers in this particular case, if there's no constant in there, so it's arguable. Then it's also increasing from +1, that's this one. So as we go from 1 to infinity on the x, the f of x is getting bigger and bigger, so it's also increasing there. So from +1 to positive infinity, it is also increasing, right? And so that's what's going on this particular picture. Now, as far as my class, what I would expect on a quiz or on a homework assignment or whatever, what I would want you to write for your answers, first of all, obviously, I want you to include this part. I would want you to do kind of like what we did on the last lesson. Give me a rough sketch. Probably use a ruler at least for that much, right? But a rough sketch of the thing, of the picture. If you want to kind of label these points, you could. Rough sketch of the picture, and then a table. You could include some of the numbers from all three of these tables into one table. You wouldn't have to include all of this stuff. You'd want like 3 values from this one, and then you'd want like 1 or 2 from this one, like going up this way, and 1 or 2 from this one going up this way. We would already have at least the ones, right? Because that's where it starts to change, right? So you'd want those changing points there, those extrema or inflection points. We'll see that in the next couple of examples. Here we go. Let's keep on going and learn the next thing. So, yep, that's what I want. So this is what we want. Now, this mess of a nonsense, this is including several different things in one space. If you want in your notes to write down definitions of some of these things, you're welcome to do so. I wouldn't stress about them being formal definitions, but something to help you understand what these things are. So we've got a bunch of things happening here. We've got the first of all, the title of what this picture is relative and absolute extrema. What does extrema sound like? It sounds like extreme. So the extremes, the biggest points and the lowest points, or the maximums or the minimums, right? And then all of these are critical points on a particular graph, and we include that because not every type of critical point is a max or a minimum. There are also points of inflection. So on something like a cubic function, right? It's always, this particular cubic function that I squiggled, right, is always increasing, right? But it does have a point where it changes, so a critical point. So in this case, it's this point where it kind of shifts the direction it's going, right? It turns it from like a negative parabola to kind of a positive parabola, right? And so the point where it shifts, the point where it doesn't change the increasing or decreasing, but the point where it changes the feel, it changes the vert. So it's like a positive parabola, and in this point and then it changes to kind of like a negative parabola. It's still decreasing that entire time, but it changes, the point where it changes, okay? So, excuse me. What about these other points? So there are 2 types of maximum. There is a relative max, which there are examples of relative maxes on this picture here, right? And here. Those are both examples of relative max. So you might just be able to figure this out from English. Relative max are where it changes from increasing to decreasing somewhere on the graph, but they may not be the absolute highest point. So the highest point on here, the absolute max, is the highest point over a specific interval that we go. Now, we should note that, like some other things we've talked about in the past, we're talking about between a given interval. So typically, we don't care that, the true absolute maximum of this entire function, if we looked over all real numbers, is positive infinity. Eventually it goes up to positive infinity, right? Eventually, and the true of the entire function over the entire domain would be negative infinity. But when we're talking about absolute max and absolute min, we're typically talking about from this point to that point, what is the absolute highest point that it gets to? And for relative, we're talking about from this point to that point, where are the points where it is at the top and then it goes back down. So where does it go from going up to going down again, right? And then in a similar vein, we have the absolute minimums in this given range, in this given domain. The absolute minimum, right, would be like this point right here. What's the lowest point that it gets to when we're looking at this chunk of the graph? And then the the relative minimum is where does it change from decreasing to increasing. So what point does it go from down to up again, right? So that would be like these points right here and right here. So that's what we're talking about. Now, all of these, again, are critical points, including points of inflection, where it just kind of jukes over, right? Something like a cubic function. Let's look at some examples that we might see with this kind of thing. So we're going to take this graph, and we are going to estimate and classify, oops, don't care about that, thanks, and classify the extrema for this, and we want to support our answers numerically. So that's, again, where we're going to make sure we include that table on there, right? So let's take a look at the graph. So we've got another cubic function, right? This is the highest exponent is a 3, so it's a third degree polynomial, a cubic function. This is really similar. So what we're going to do is, the first thing we're going to do is we're going to estimate this. So we're going to take a look at this graph, and we're going to make a guess where it changes. So those inflection points. So where does it change? Well, it looks like it changes at, oops, I need to move this up here. It changes. Now, on this picture, it looks like it is less than a half, but we're gonna do like we did what it suggested on the first one, and we're gonna go to the nearest half. So the nearest half, as far as our changing point here, what is happening? Why is it? Is it behind? Oh, it is behind. What did I do? I thought I fixed that. Beautiful. I probably undid too many things. So the nearest is a half. So we're going to estimate, starting with, let's kind of color code what we're doing. So we're going to estimate that it is increasing from negative infinity to a half, and from, looks like 1 to positive infinity. And then it is decreasing from 1/2, not 1.5. Oh, I did that wrong, didn't I? Sorry. How about negative 1/2? Thanks for your help. Good job. If I was doing this lesson live in a class, somebody would have already been, don't you mean negative 0.5? Yes, in fact, I do. From negative 0.5 to 1. Right? So supporting our answers numerically, I may need to move stuff. I don't remember where I put the table. Let's pull up a table or two, right? So we've got, yeah, okay. I made a couple of different tables to kind of give us our two different intervals. So this table is for the decreasing bits. Let's pull this up. This table right here is, what you doing, Willis? This table is for the decreasing bits. So from negative 0.5 to 1, it is going down. So it's going from 1/8 to 0 to whatever that is, 5/8, right? To negative 5/8, so still going down, to negative 1, so it's still going down. And then it starts to go back up again, right? So in the table that we would write, we would probably want to include those values. So let's go ahead and build the table on this one. So x and then f of x. So for the decreasing bit, which we probably want in the middle of our table, so I'm going to do the increasing bits first. So I'm going to put, how about negative 300? Sounds good. So at negative 300, it is at negative 27,000 2.7 times 10 to the, what is that? 27 million. 1, 2, 3, 4, 5, 6, 7. 10 to the 7th. And then at there, we've got negative, let's put a -1 in here. At -1, it is at -1. And then, oops, at -0.5 is where it changes. That's our local maximum, right? Oh, we're supposed to be classifying the maximum and minimum. We'll go back after we fill in this table and we'll label what these are. Yeah, forgot what we were doing. I was just writing inflection points, changes and things. But we'll do this. We'll do it in different order. Here we go. So at 0, it's at 0, and then we'll include the 1 on there. At 1, you could include the half if you wanted a little bit more granularity. At 1, it's at -1. And then at 1.5, it is at -0.4. And then something over here, so let's do 300 again, why not? It is at positive 2.7 times 10 to the same thing, 10 to the 7th, right? So that's what's going on here. Let's change our labels, or let's at least add a label. So this point right here is nothing. But at this point right here, so the relative maximum, relative max, we just added extra information to this problem. It's no problem, no big deal. We're so smart to do extra stuff or something. Is at 0.5, -0.5, almost did it again, 0.5. And where is that? That is at 0.125, or an eighth. So there's a relative maximum right there. What about the relative minimum? That's this one over here. Relative minimum, which is at 1, -1. And our support is the picture and our table. Great googly moogly. Okay, so I don't think it'll be that big a deal because of type of mic and everything else, but I just turned my fan up. So if there's more terrible noise, I apologize. But let's go on to the next thing. All right. So another type of problem that might show up is one that's written like this, where it says to use a graphing calculator to approximate to the nearest hundredth the relative absolute extrema of f of x equals -4x cubed minus 8x squared plus 9x minus 4. State the x value at which it occurs. So basically what that means is we want the entire point. We want the where it is, what the height or the depth it is, the local max, the local minimum. I'm using different vocabulary. Local and relative. Local minimum, local maximum are other words you'll see in other textbooks and whatever else. Relative maximum, relative minimum are what we're using, except when I accidentally say the word local. But on this one, it says use a graphing calculator to do it. So what I'm going to show you is another thing, another tool that your calculator almost certainly has in its tool belt. So let me pull up my calculator. All right, I've pulled up my calculator and I also graphed the thing. So I plugged it into my equation editor. That'll be different place for you. And then I graphed it, and mine probably looks a little bit different than what yours looks like. I kind of did a weird thing with the windows. So let me bring up my window settings. Again, you're going to have to do this differently on yours. So I went from x, -8, to +8. And you see I did a different range of values for the y parts. Just to be able to see the graph better. So I went from -25 to 15 on my window, and I just counted by ones. And so that's how I made this look like this. And so you almost certainly have a tool that lets you find a maximum or a minimum between a particular spot. And so we can tell that we have a local minimum right here. So if we use whatever your trace function is on your calculator, you can kind of get a little bit of a guesstimation, but it's going to be hard to get that clicked right into the exact spot and whatever else. But your calculator almost certainly has a way to calculate a relative minimum or relative maximum based on what you're going to do. And so you're going to have to figure out how to do this on your calculator. You can look it up. If you want to put down in the comments below what kind of calculator you have, I'd be happy to make videos teaching you how to do it. But there's somebody else that's already done that somewhere. I am quite sure of that. So let's see what it typically looks like. I'm going to do it on this calculator. You try on your own, and we'll see how we do. Okay, so I paused and popped this up because I had to double check, make sure I remember how to do it on this calculator. And in so doing, I realized I remembered that it's actually the method for doing it is actually easier on this calculator, because the real version and the emulator of this calculator, it has a touch screen, and so there's less button presses. So like for example, on this one, you just have to hit function and Extrema, and then you can kind of click where, and then you can tell it where you want it to be, or you get close and then hit Extrema, and it'll add that picture on there, and it'll tell us where it is. And so there's less button pushes and all of the things, and it'll leave that on the screen. And so on like the TI-84 or the Casio calculators that some of us are using in my class, there's a few more button pushes. And so I'm going to describe on this picture what you're going to end up doing. You're going to end up, there's going to be a button. It's probably going to be in like a calc menu or something along those lines. And it's going to have a button that says maximum or a button that says minimum. And what you have to do is you click that, and then it'll bring up like a dotted cursor on the screen. You probably can't see that very well. Let me get a darker color. So it's going to bring up a dotted cursor on the screen, and then you're going to have to use your scroll wheel or your push buttons to move that. And what it's going to say on the screen is something like lower bound or upper bound, probably lower and then upper. And so what you're going to do is you're going to want to take and move that cursor to someplace kind of like where I put it just now. Move it to the left of where you're wanting to find the in this case minimum for, and then once you push enter or execute or whatever it is, it'll bring up another cursor, and it'll say max or upper bound or something along those lines. And so you're going to move it over to the other side. Oops, we don't want that on there. Move it to the other side of where it is, and then you're going to push enter. And so what it's doing is saying, where do you want to find this local? Where do you want to find this minimum at? I want to find it, and so it's going to tell you you're words. Sometimes they're hard. You're saying, I want to find it between this point and that point. And so that is typically what you're going to do on a lot of graphing calculators, not the one that I'm showing you. So it's going to be something like that. So we discovered, let me pull up my calculator again, that it has a relative maximum at 0.42. We're supposed to round to the nearest hundredth, so 0.26. So a max, I don't know what I'm doing, a maximum at 0.426. Is that what I just said? 0.426 negative 1.27. To 927, right? So that's the first bit. So it's worth noting and making sure for understanding the the relative maximum is this. This is the highest that it gets. And its corresponding x value, if this was in like a physics class or something, is probably be the corresponding time. At time 0.43 seconds, 426 seconds, the thing was negative 1.927 feet underwater or something along those lines, right? And so that's what we're talking about there. Excuse me. So then it also has a local minimum. So we're going to I'm going to click over here and bring it up at that point. So when you go through the process and find the relative minimum, it's at negative 1.60. Yeah, negative. So it's got a minimum at negative 1.760 because of rounding. And the actual minimum is negative 22.814. 2.814. There we go. We just got a couple more things left. I think the next few things are the junk that I just wrote. Yep, that, and then more junk. And then here we are. We got 2 slides left, and we're through. So average rate of change. So this has got less on it. That's actually intentional. I didn't forget this time like some of the things on the last video. It's actually intentional because I wanted to talk through this and then kind of add a formula as we go. So when we've talked about rate of change in the past, we've talked about linear functions. So something like this, right? Oops. Adding some weird cultish shape. That was not intentional. So we're talking about, in a linear function, we're talking about rate of change is the same as its slope, right? It's rise over run, all the things that you've learned since probably pre-algebra and definitely since Algebra 1. That's what we're talking about there. So if you have a shape that isn't linear, so something like this inverted parabola, right? Then its rate of change changes. The rate of change changes. And this is the heart of something called a derivative, which you'll learn about in calculus, right? And you'll learn how to find it find what the average rate of change is at a given point and all of these things. So we don't know how yet until we learn about derivatives. We don't know how to figure out what it is at this specific tangent, right? So we just have to figure out what the average rate of change is. So we're going to, if it was linear, we would use this formula, right? We would use m equals y2, so the difference of the y's, minus y1 over the difference of the x's. That's the slope formula, right? We've been using that for ages. Whoop, I can write. We've been using that for ages. That's no big deal. That's how we calculate slope, which is rate of change of a linear function. So here, to find the average rate of change with what we know so far, we want to know how much average. We don't care about all this bump. We want to kill off all of this and just figure it out between here. So it's the same thing, basically. It's just slightly different because this thing doesn't have a constant rate of change. It's not linear. And so to find rate of change, we modify the formula ever so slightly. So to find the rate of change, the average rate of change, we do the same-ish thing. So for the x part, it's just fixed. This to this, right? So the x part, we just have x2 minus x1. It's just the difference of the x's. Easy peasy lemon squeezy, right? For the y part, we have to take into account the shape of the function. It's not just the y minus the y, but I mean, it kind of is. But we probably don't know these numbers right off the bat. We're probably not given just 2 points. We're probably just given a function and a range of values. You'll see when we do this in an example. So instead of just being y2 minus y1, it's f of x2. So the y that corresponds to x2, which is the same thing. We just have to take the function into account, so we got to do a little bit more math to get us there, minus f of x1. So again, it's the same thing because y is the same as f of x, right? It's just a different notation, so it just gives us more detail. So rate of change, and this actually, you could say that this formula is actually the same as the slope formula, right? It's the same formula. It's just that what the function we're doing isn't quite so simple, so we have to get more specific. Let's do an example or two to make sure we understand what's happening, and then we'll be through with this lesson. So we want to find the average rate of change of this function. So You probably know from Algebra 2 and then even just from this lesson that this is going to be a negative cubic function. So if we were to graph this, it would probably look something like this. It might just have an inflection point right there. Something. It's going to be one of those two, something. We could do points. You probably aren't familiar enough to be able to just jump. Oh yeah, this is definitely going to be one or the other. We don't care, right? That's not what we're worried about. What we need to do is we need to just use that formula that we just learned to figure out what the average rate of change between these two intervals is. So between -2 and -1, what is the average rate of change? So the rate of change, we're going to write it in generic terms, and then we're going to actually find the things, and then we're going to, do the numbers. Rate of change is x2. So this one, the -1. Now, it's worth noting, this is not a point. It's a range of values. It's a domain restriction, right? So x2. So these are both x numbers, not x and y numbers. I don't know what I'm doing. Minus x1, so the first x, over f of the second x, so -1, minus f of the first x, -2. So that's what we're going to find. Now we know how to find f of -1, right? We just plug it in -1 into the function. So f of -1 is -1 cubed plus 3 times -1. -1 cubed is -1. -1 is +1. Remember that when we raise a negative to an odd power, it stays negative, right? That's what we're doing there. So -1 times negative is +1, and then -3 is -2. Oops. So what about f of -2? We're going to plug a -2 in there. So negative. It's probably going to take one more line to get it there because it's not quite as easy on there. Well, maybe it is. Minus. Is it minus? No, it's plus 3 times -2. -2 cubed is -8 times negative is +8. And then -6, because 3 times -2 is 6, and that equals -2. So now plugging those numbers in up here, plugging those numbers in up here, this one is -2 minus, are they both -2? Is that true? Did I make a mistake? Who knows? Let's see. I did make a mistake. Did y'all already catch it? It's this one right here. Or is it? No. Just kidding. The mistake was even stupider than that. You almost certainly caught it. That 8 minus 6 is in fact +2. We all make mistakes. I hope this helps you. I say this in these videos sometimes. What bears mentioning again. I hope this shows you that just because you make careless mistakes sometimes doesn't mean you're bad at math. So -2 minus 2 over, and we'll go ahead and do this in the bottom. We got to ka-chink that. -1 plus 2 is +1. So this is -2 minus 2 is -4. So the average rate of change in this interval is -4. -4 over 1, if you prefer all of those things. All right, last example, and then we are out of here. Okay. So on the interval 0 to 1, right? So I'm going to do this example, and I'm going to kind of write it in a different way a little bit. I'm going to write it all as one big equation. You can do either of these. Oftentimes in a textbook, both like math books and science books, they'll do it like this way. Sometimes I think it's a little bit easier to break the problem up into steps and see what goes on, but you do whichever makes the most sense to you. So we're going to have f of, f of 1. So what is f of 1? We're going to plug in 1 into these places. So it's going to be negative 1 cubed plus 3 times 1. All right, so that's f of 1. Yes, 1 plugged in there. Minus f of 0. That's a nice one. We like zeros in these. Zeros make stuff poof. That's very, very handy. You can probably figure that out in your head, but make sure you show your work, especially because if you make a little mistake like what I did, it's going to be a lot easier to figure out what in the world went wrong if you will show what you did, because then you can track your brain backwards because you took your brain and you put it on the page, right? Over the difference of the x's. So 1 minus 0. That's also easy peasy. So we're going to do this the same sort of way, right? But we're going to work it out. We're going to do it all kind of in one big jumbled mess instead of breaking it up into individual pieces. So negative 1 cubed, negative 1 cubed. 1 cubed is 1, and then negative 1 is negative 1. 3 times 1 is 3. Whoops. I can write. Who said I can't? You? It's fine. Don't worry about it. No big deal. This one is great. We love it. Negative 0 cubed is 0. 3 times 0 is also 0. I love it. That's such a wonderful thing. 1 minus 0 is still just 1, so who cares about the denominator? So our final answer is just this first bit, negative 1 plus 3, which is in fact 2. So the rate of change from that interval is 2. And that, believe it or not, is it for this lesson. Look, under 45 minutes, barely. There's a lot in pre-cal. You got this. Hang in there, stick it out. It's a marathon, not a sprint. Pace yourself. Do the work. I'll see you in class. Don't forget to like, comment, subscribe, whoever the heck you are. Adios. Bye-bye.